Now that we've got a little bit of information about three of the quantum numbers, let's talk about the relationships between some of these sublevels and some of the orbitals in these sublevels. So I think we're pretty familiar with this, but it's worth covering the relationship between 1s, 2s, and 3s. So if we were to draw them on a set of axes, of course it'd be 1s would be the smallest, 2s, and 3s. Again, not necessarily drawn to scale, but doing our best. So each value of n for the same sublevel just gets bigger. And we'll see that for 2p, 3p, and 4p as well. They're all the same shapes, they're just getting bigger. And again, these s's go all the way out to 10s, etc., though we won't need all of the s's for the current periodic table. The relationship between 2s and 2p, well, the short answer is that 2p fits within 2s. And so that means that if I draw 2s, similar to what I've just done above, then I'll label it 2s. Then 2p doesn't touch the nucleus. And it fits, again, within the same space. If I define these as x and y, then this is going to be 2px along the x-axis. And so here's what I mean when I say that 2px, it is in the same volume. So 2px is in the same volume as 2s. And our picture of how this atom is forming is that in 1s, the sphere is sufficiently small that you can only fit one orbital. But then 2s is 4 times larger, and you can fit 2 electrons in a sphere, but you can also fit electrons along each of the axes in these more complex shapes. What we will see is that typically 2p is a higher energy way of putting the electrons in. But remember, the electrons still want to be as close to the nucleus as possible. And so by stuffing more electrons into this n equals 2 volume, this 2s sublevel, you're keeping them as close as possible to the nucleus. So they're in the same volume, and so 2px is another way to put electrons into this n equals 2 principal energy level, which is inside the 2s sublevel. Okay, and what you might imagine, and let's go ahead and sketch it out. So if we had n equals 3, let's see how this works. To make sure we're on page, good. So let's say n equals 3 is here, roughly. Then what we might draw is we might draw 3px. So 3px, we have 3s. And then, at least drawing one of the 3Ds, one of them comes in and has 4 parts. Again, it should end at the same place as the 3s. And so this one I think is going to be 3D x squared minus y squared. And the designations are not important. Let me take a look here. 3D x squared minus y squared. And so the 3Ds are more complicated ways of fitting electrons into the same sphere for n equals 3, which is defined by the 3s sublevel. And remember, n equals 3 is approximately 9 times larger than n equals 1. So there's more space. So there's more ways of putting the electrons in. Okay. And that continues on. But for now, let's talk about the p and d orbitals. They have lobes, that's what we're going to call these pieces, with different phases. And so let's just draw what I mean by that. So we'll draw on the x-axis, we'll draw, let's just say 2px. And because these are based on wave functions, and waves have both positive and negative places, and so let me just draw a wave. Waves have positive and negative spaces in them, and that's just a handy way to keep track of the top and bottom of a wave. If we turn the wave upside down, then we could also call this positive and this negative. And so from that standpoint, all we're saying is there are different parts to this wave and this wave function when we're talking about psi. There will be positive and negative lobes or portions of orbitals. And this will be important when we talk about constructive and destructive interference of orbitals later on. Okay? And so you'll sometimes see them with different colors in them or with pluses and minuses in them to tell them apart. If you have 4 parts, there will be 2 positive and 2 negative lobes for a d orbital. Now, describing an orbital, before I go on, let me just say that each orbital will hold a maximum of 2 electrons. It can hold less, it can hold 1 or 0, but each orbital will hold a maximum of 2 electrons, and that's why we're building up this picture of orbitals, so we can know what spaces the electrons are in and then put the electrons in. So here's n equals 1. We have a 1s sublevel with 1 orbital. For the second principal energy level, we have 2s and 2p with their orbitals. And with the third level, there's n equals 3, third principal energy level. Then there are 3 sublevels with 1, 3, and 5 orbitals in each. And so this is a nice handy summary of some of the things we've already said with their quantum numbers as well. Okay? All right. Question then, what are the quantum numbers and names, for example, 2s, 2p, of the orbitals in the n equals 4 principal energy level? How many orbitals exist? Well, so for n equals 4, we said L equals 0 to n minus 1. That means it's going to be L equals 0, L equals 1, L equals 2, and L equals 3. And then we said that M sub L equals minus L to plus L. So that's just going to be equals 0. So one number, and we'll say 4s has 1 orbital. M sub L equals minus 1, 0, and 1. So 4p has 3 orbitals. Continuing on, 4d has 5 orbitals, and 4f has 7 orbitals. And if you look at some of the previous pages, you can show that. For a total of 12, 13, 14, 15, 16 orbitals in n equals 4. And as a note, for n equals 4, if there are 16 orbitals and each orbital can hold a maximum of 2 electrons, there's a max of 32 electrons in n equals 4.